Very good evening to all. I welcome you all for today's session by Dr. Anand Chitrao, sir. Over to you, sir.
Yeah, thank you, madam. Um, so let us begin this session uh, by some doubts. Do you have any questions? Anybody? Yeah, is my screen visible?
Yes, sir, the
Yes,
screen
sir.
is visible.
Okay, sure. Then if there are no doubts, let's start with today's session. I'll do a small recall on semi-direct products. And a few examples. So can somebody tell me what's the definition of a semi-direct product? So you start with two groups, let H and N be two groups. Suppose we are given a homomorphism theta from H to ot N. Does everybody remember what ot N means?
Yes, sir. An automorphism from a group to itself.
Yes. So this is the group of automorphisms, a group of isomorphisms from N to itself. There is a group under which operation? Ot N is a group under? Yeah, composition of functions. Then we can construct a group denoted by this symbol N cross H in this angled alpha, where the group operation is as follows. So suppose you are given N comma H. So the underlying set of this semi-direct product is N cross H, the set theoretic Cartesian product of N and H. And the operation is as follows. So take any element N comma H, take any other element N prime comma H prime. Their product is, so first write N over here. Instead of multiplying that with just N prime, you multiply that with theta applied to H further applied to N prime. And in the second coordinate, this is the usual multiplication. Is this clear?
Yes, sir.
Okay. So let us see some examples. So Bn, does anybody does everybody remember what Bn is? Bn was defined to be,
Upper triangular matrices.
yes, the group of upper triangular matrices in GLNFP. Okay. Then what is Tn? It was defined to be the group of diagonal matrices in GLN FP. And finally, UN was what was UN?
The lower triangular matrix, set of lower triangular matrices.
No, the group of upper triangular matrices, but ones on the diagonal. Those are called as unipotent matrices. In GLNFP. Okay, does everybody know what this is? It's the set of all matrices of this form 1, 1, 1. Then anything on the upper half of the matrix, in the upper half of the matrix, and zeros here in the bottom half. Okay, is this okay?
Yes, sir.
Yes,
Yeah.
sir.
Now, turns out Bn is isomorphic to a semi-direct product of this form. Un semi-direct product Tn. Okay. The point to note over here is that their cardinalities match, first of all. Bn, the cardinality of Bn, if you check, that's the same as the product of cardinalities of Un and Tn. And then there's a small check how Tn acts on Un via this automorphism. So let us see this in the example of n equals 2. The trick is this this homomorphism theta from H to aught n is supposed to be conjugation by elements of H on n. Okay, it's supposed to be conjugation by elements of H on n. So let's compute that via this prescription. So compute theta from Tn to aught un. So let us start. Given an arbitrary element of Tn, it looks like this, A00B, right? An arbitrary element of Tn looks like A00B. An arbitrary element of Un looks like 1U01. And you have to conjugate 1U01 by A00B. So let's do that. So what is this equal to? Can somebody tell me what is this equal to?
Sir, is it diagonal 1 and B inverse? Other diagonal are 0, 0.
1 B inverse 0, 0.
Yes, sir. I am in outside. I am not calculating on just my mind. I am not using pen and
Yeah,
paper.
but
Sorry.
okay then, fine. Somebody else? It's just a plain matrix multiplication, right? What's the product of the first two matrices? So A, then AU, then 0 and B. Then you multiply that by A inverse 0, 0, B inverse. What do you get? So this entry is 1. The next entry is A by B times U. Then the next entry is 0. And the final entry is 1. So what happened over here? So yeah, if you start with an element of Tn, that's A00B, that is sent to the automorphism of Un, which just multiplies this U by A by B. Okay?
Yes, sir.
Yeah. So that's this automorphism. So is this clear?
Yes, sir.
Yeah. Now tell me if anything is different, if I replace these by real matrix groups. Suppose I take Bn to be the upper triangular matrices with real entries. I take Un to be upper triangular unipotent matrices with entries in real numbers, and Tn is the diagonal matrices with entries in real numbers. Will anything change here?
Sir, can you repeat the question?
Yeah. So suppose I replace these groups by their real avatars. So if I take upper triangular matrices over the real numbers, I take upper triangular unipotent matrices over real numbers and diagonal matrices over real numbers. Is this result still true?
We have to exclude 0 from real number, maybe.
Yeah. So BNR is the subgroup of GLNR of upper triangular matrices. Similarly, UNR is the subgroup of GLNR of upper triangular matrices with ones on the diagonal. Similarly, TNR. The answer
Sir,
is
what is
still
the
yes.
TNR stands for?
Yeah, this is diagonal matrices with entries in real numbers. TNR is the
Okay.
subgroup of GLNR consisting of diagonal matrices. So the point is this result is still true because you saw over here, it doesn't matter what A, B and U are from, right? This is like a formal identity. When you conjugate 1U01 by A00B, the U entry gets multiplied by A by B. So it doesn't matter what field you are in, this result is still true. You can replace this R by any field you want.
Sir, this result is for non-zero real number or for all real number?
What does that mean?
Sir, in the product, there is A by B of U. So if B gets 0, then it becomes undefined.
Yeah, but
I'm thinking like,
this Tn is inside GLNR, right? If B is 0, then is this matrix invertible?
no, sir.
Yeah, when we are saying this is contained in GL and R, that means A and B both are non-zero.
Got it, sir.
Okay,
Okay,
sir.
great. Yeah. Next example. Does everybody remember Dn? This is just a recall. Dn is isomorphic to a semi-direct product of this form. Zn semi-direct product Z2. Okay. Dn is isomorphic to Zn semi-direct product Z2. So what's the homomorphism theta in this case? Zn is the subgroup generated by R. Z2 is the subgroup generated by S, if you remember from Dn. What is theta in this case? What was the trick I told you about? Theta is supposed to be conjugation on this group by elements in this group. Okay. So all that you have to compute is how S acts on R by conjugation. So what's the answer over here? What is S, R, S inverse?
R inverse.
Yes, R inverse, right? So this homomorphism, which is determined by where a generator goes, sends S to the function which sends R to this is supposed to be conjugation. You just computed it. So what's the answer? Just tell me.
R inverse.
Yes,
R inverse.
R inverse. So the homomorphism theta in this case sends S to the map sending R to R inverse. Okay. Next, Sn is a semi-direct product of An with Z2. So yeah, so even our familiar group Sn or the master of all finite groups Sn is a semi-direct product of this form An and Z2. Try to compute the homomorphism theta in this case, okay, as a homework. Just use the trick that theta is supposed to be conjugation by elements of here Z2 on An. Now, just to give a non-example, Q8 is not a semi-direct product. Yeah. So just to tell you why, the point is whenever you take semi-direct products, uh, here this is N and this is H, the intersection of N and H inside the new group you constructed is trivial. Okay, it consists of singleton identity. this is N, this is H. In the Cartesian product, they don't intersect, right? They only intersect at identity. So it's a necessary condition. If a group is a semi-direct product, then it's necessary that it has two distinct subgroups which intersect trivially. That's not the case in Q8. Any non-trivial subgroup means non-identity subgroup of Q8 contains 1 and -1. So therefore, Q8 cannot be a semi-direct product. Is this clear?
Yes, sir.
Yeah. Then we'll move on to a slightly advanced topic, Sylow's theorems. Let G be a finite group and P be a prime number. A Sylow P subgroup of G is a subgroup H of G such that, so the first condition is cardinality of H is a power of P. And the second condition is that that's the highest power of P dividing the order of G. So you can say that P doesn't divide order of G by order of H. And just to be consistent, just write this as order of H. Is the definition clear? Start with a finite group and a prime. A Sylow P subgroup of that finite group is a subgroup H satisfying these two conditions. The subgroup has to be a P group, which means its order has to be a power of P, and that subgroup should be the largest one. So P shouldn't divide the order of G divided by order of H. Okay? Let's look at some of the examples. Can you tell me what's a Sylow 3 subgroup of,
It is
yeah, any doubt? Okay. What's a Sylow 3 subgroup of Z6?
Z3.
Z3, yeah, but as a subgroup, what is it?
0 to 4.
Yeah, is this subgroup generated by 2, 0 to 4. So why is that true? Is it clear? You have to check two things. Order of the subgroup generated by 2 is, how many elements does it have? 0, 2 and 4. So the order is 3. And what's order of Z6 divided by order of 2 bar? 6 by 3 equals 2. 3 doesn't divide 2. So the second condition is checked. Second example. A Sylow P subgroup of SP, the symmetric group on P symbols, is can somebody tell me? So what is the cardinality of a Silo P subgroup of SP? What should be the cardinality?
P to the power
P
k.
factorial.
But what K? So it should be a P power. That P power should divide the order of SP, right?
Yes.
Yes, sir.
So what's the largest power of P dividing the order of SP? Order of SP is P factorial. So we know that P definitely divides P factorial. But does P square divide P factorial?
No.
Yeah. So the largest power of P dividing the order of SP is just P. So you just have to find a subgroup of order P. So what's a subgroup of order P in SP?
Generated by n side.
What? Sorry,
Side.
your voice is breaking. Can somebody tell me the answer? What's a subgroup of order P in SP? So you can take this subgroup generated by a P cycle. What's the order of this element? 1, 2, 3, dot, dot, dot till P. What's the order of that element?
Sir,
So
P.
P factorial divided by P.
The order is just P, right? It's a P cycle. N cycle has order N. So a P cycle will have order P. The order of 1, 2, 3, dot, dot, dot till P is P. So the subgroup generated by this element is of order P. Therefore, it's a Silo P subgroup of SP. Is this clear?
Yes, sir.
Yeah. Then so you saw the examples of UN, BN, and TN. So it turns out UN is a P silo or silo P subgroup of BN. Why is this true? What's the order of UN?
5 of n.
No, UN in this case, uh, it's not U of N, right? Let me repeat. UN is the subgroup of upper triangular matrices with ones on the diagonal. subgroup of GLNFP of upper triangular matrices. So now what's the order? We computed this, I think, in the first or second lecture.
Yes,
Sir,
sir.
P
P
to the
to the
power
power n into n
n
minus 1
times
by 2.
10.
Right, great. What's the order of Bn? Does everybody
P1,
remember what Bn is? It's the subgroup of upper triangular matrices. So what's the order?
P to the power n minus 1 into P to the power n into n minus 1 by 2.
No, P minus 1, right? On
Oh,
the
yes, sir.
diagonal, you only have P minus 1 things. So P minus 1 to the n, rest of it was correct. P power n into n minus 1 by 2. Now can you see why un is a silo P subgroup of Bn? The order of un is a P power and order of Bn divided by order of un is just P minus 1 power n, and P doesn't divide P minus 1 power n. Okay?
Yes, sir.
Yeah, great. So now let me tell you the three important theorems of silo. First one is every finite group G has a P silo or a silo P subgroup. Both are the same. Sometimes P may not divide the order of G. In that case, the P silo is just singleton identity. It satisfies both of these conditions. That's why here K is taken to be greater than or equal to 0. So first theorem is every finite group G has a P silo. Second, all silo P subgroups of G are conjugate by elements of G. What does this mean? This means that if H1 and H2 are silo P subgroups of G, then there exists a little g in capital G such that G H1 G inverse equals H2. Okay? And the third theorem is if we write the order of G as P power n times m with P not dividing m, then if you let np equal the number of silo P subgroups of G, then this NP will divide whatever is left. If you take out as many P's as possible from OG, so NP divides M, and NP is congruent to 1 mod P. Is this clear? The statement at least?
Yes, sir. Clear.
Yeah. So you write order of G as some p power times some prime to p part, then the number of silo p subgroups, this number divides this prime to p part, and the number is congruent to 1 mod p. Yeah. So this theorem is useful in the classification of groups of a given order. As an example, let's do this theorem. Let's prove this theorem. Let P less than Q be primes then every group of order PQ is abelian. Sorry, yeah, I forgot a condition. If P doesn't divide Q minus 1, then every group of order PQ is abelian. So how does one show this? Let's see a proof. So P and Q are primes dividing the order of G. So let's start with let G be a group of order PQ. Define N, capital N, to be a silo Q subgroup of G. Okay. And H to be a silo P subgroup of G. Now tell me, how many silo Q subgroups are there? Let's start. Let NQ be the number of silo Q subgroups. Then what do we know? We know that we know from Silo's third theorem that NQ divides, what should it divide?
P.
Yeah, NQ should divide P, and NQ should be congruent to 1 mod
P.
Q. It's a Silo Q subgroup, right? Silo, if it were a Silo P subgroup, then 1 mod P. Since we have a Silo Q subgroup, 1 mod Q. So what are the possibilities of NQ satisfying these two things? So the first condition says that NQ divides P, and NQ is a number of silo Q subgroups. So NQ has to be 1 or P, right?
Yes, sir.
P is a prime, so NQ has to be 1 or P. So let's check if 1 or P satisfies this. So 1 trivially satisfies this condition, but does P satisfy this condition? P does not satisfy this condition because P minus 1 is a number smaller than P, which is smaller than Q. So Q cannot divide P minus 1. So this forces NQ to be 1. Is this clear?
Yes, sir.
Yes.
Yeah. Next, theorem 2 then implies that N is a normal subgroup of G. How do you see this? What does theorem 2 say? Theorem 2 says that all silo P subgroups of G are conjugate. Actually, you don't even need theorem 2. You can directly see N is normal in G. How do you see that? Given any little g in capital G, the claim is little g n G inverse is a silo Q subgroup of G. Do you see this? First of all, conjugate of a subgroup is a subgroup. Then the order of G and G inverse is the same as the order of N. So that says the order of G and G inverse is a power of P. And then we have to show that Q doesn't divide order of G divided by order of G and G inverse. Order of G divided by order of little g n little g inverse. This is the same as order of G by order of N. And we knew that N is a silo Q subgroup, so P doesn't divide this. Sorry, Q doesn't divide this. So this says that G and G inverse is a silo Q subgroup. But how many silo Q subgroups are there? There is a single silo Q subgroup. So this implies N is a normal subgroup because this implies G n G inverse equals N, and then N is a normal subgroup of G. Okay. Next, we we had set H to be a silo P subgroup of G. So this implies the order of H equals P. Now, what's the order of Hn? Note that N is a normal subgroup and H is any arbitrary subgroup. Therefore, Hn is a subgroup of G. You can show this happens. What's the order of Hn? So there is a small formula which says order of Hn is order of H times order of N divided by order of H intersection N. Now, H intersection N is a subgroup of both H and N. Therefore, its order must divide P as well as Q. But P and Q are distinct primes. So order of H intersection N is 1. So this is just PQ. So this implies that G equals Hn, or maybe I'll write it in a different way, NH. We have already checked that N intersection H is trivial. So you can conclude that G is a semi-direct product of N and H. G is isomorphic to a semi-direct product of N and H. Now all that remains to see is that this is a direct product, right? Why? N has order Q and Q is a prime, means N is isomorphic to ZQ. H has order P, therefore H is isomorphic to ZP. So we are taking a semi-direct product of two abelian groups. This product is abelian if and only if the theta map is trivial. G is abelian if and only if theta from H to aught N is trivial. Now what is H isomorphic to? We said it's isomorphic to ZP. And what is N isomorphic to? ZQ. So aught N is isomorphic to ZQ star. Now, how many homomorphisms are there from ZP to ZQ star? Yeah, you can also say this is isomorphic to ZQ minus 1 directly. How many homomorphisms are there from ZP to ZQ minus 1? What's the formula? The number of homomorphisms between two cyclic groups is?
GCD of P, comma, Q
Yes,
minus.
exactly. The number of homomorphisms is the GCD of P and Q minus 1. But we saw that we assumed that P doesn't divide Q minus 1. So therefore, there is a single homomorphism, and that's the trivial homomorphism. Number of thetas equals the GCD of P and Q minus 1, which equals 1 since P doesn't divide Q minus 1. So therefore, this theta is trivial, which means G is abelian. So this proof uses a lot of concepts that we learned over these 3 days. Okay? Any doubts till this point? If not, we can move ahead. So that's all I wanted to teach. Let's look at some practice questions. So now I want a lot of responses from your side. These are quick questions. Find,
Sir,
yeah,
sir, in the, can you Just like the
Sorry,
above
can you
state, sir.
type what you're saying because your voice is breaking. Yeah, find an element of order 42 in S13. What's the answer?
Sir, 4.
Yeah, what's the answer?
Sir, is it 4?
4. What does that mean? Yeah, S13 is the permutation group. You have to tell me a product of cycles whose order is 42. How do you compute the order of elements inside S13?
Sir, we will first partition the number 13, just like 7 and 6. So
Yeah,
there some will be 13, and then what we need to do is that we write n factorial, like here 13 factorial divided by the cycles. That is, we will see how many times. Uh, Sir, something like, actually it was something like that. I forgot actually.
We have to
no,
take
but you're on the right track. So the point is you factorize 42. 42 can
and
be written as 6 times 7. Yeah,
sir,
what's the answer?
after this we can take a LCM.
Exactly. You note that 6 and 7 are co-prime, so their LCM is equal to their product. So if you are able to get two disjoint cycles in S13, one of order 6 and one of order 7, then you are done, right?
Yes.
Yeah, is that possible? What's a cycle of order 6? 1, 2, 3, 4,
4,
5,
5, 6.
6. Yeah. And now what's a disjoint cycle? What's a cycle of length 7 disjoint to this?
7 to
7
13.
to 13.
Yeah, 7 dot 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 13. So if you take sigma to be this element, then order of sigma is the LCM of the order of the first cycle, which is 6, and the order of the second cycle, which is 7. This is 42. So that's how these problems are solved. Second, uh, find an element of order 42 in S12. Is that possible? Do the same trick. Now 6 plus 7 won't work.
3 to
So try
7
to
work.
what?
3 to 7.
Yes, yes. So you write 42 this time as 2 times 3 times 7. Then note that 2 plus 3 plus 7 is 12. So you can find a product of disjoint cycles in S12 with cycle type 2, 3, 7, right? So that will tell you the answer. Then the third problem. Find the remainder when 5 power 2025 is divided by 11. So how do you solve this?
Sir, we can take 5 square is congruent to 5 square is 25.
Yeah,
So we'll 5 square is congruent to 3 mod 11, and then we'll raise the power.
yeah. But using group theory, you can simplify that computation a lot, right? So what you do is you note that 5 is co-prime to 11. So 5 bar is an element in Z11 star, right? What's the order of Z11 star? Units inside Z11? What's the order of Z11 star?
So 5 of 11.
Yes, 5 of 11. What is that?
So
10.
10.
10. Now, the order of an element divides the order of the group. That says order of 5 divides 10, means 5 power some number is 1, and that number divides 10. So this means 5 power 10 is congruent to 1 mod 11, right?
Yes.
So you separate this power, you separate out the largest multiple of 10 from this power and look at what's left. So you know that 5 power 2020 is congruent to 1 mod 11. So you just need to compute 5 power 5. Okay?
Is 4.
Yeah, 5 power 5 is 4, you're saying? So let's see. 5 power 5, write that as 5 square, 5 cube. So this is 25, which is 3, and this is 125, which is 4, right? So that's congruent to 12 mod 11, which is 1 mod 11. So the answer is 1. So yeah, 1. Is that clear? There are some
Yes,
chats.
sir.
Okay, no problem. So consider the group which is bijections from R minus 0, 1 to R minus 0, 1. Okay? Consider this a group of all bijections from R minus these 2 points to itself. Now I'll tell you 2 elements in this group. F, which is 1 by Z, and G, which is Z minus 1 by Z. I'm looking at this group under the operation of composition. So what's the order of F? Quickly do this computation and tell me. What's the order of F? Is F the identity map? No. So the order cannot be 1. What is F square? You have to look at F composed with F of Z. So that's F evaluated at Fz.
It is
That
Z.
is, yeah, it's just Z. So that implies order of F is 2. What about the order of G? G is not the identity map. So you have to compute G square. Turns out the order of G is 3. The order of G is 3. Now, I want you to compute F G F inverse. So let's do this computation together. F inverse is just F. So you'll have F composed G evaluated at 1 by Z. This will be F evaluated at 1 by Z minus 1 upon 1 by Z, which is F evaluated at did I do this correctly? This is Z minus 1 and F applied to Z minus 1 is 1 upon Z minus 1. I want you to check that this is the inverse of GZ. I want you to check that this is the inverse of GZ. So this says FGF inverse is G inverse. So what is this subgroup generated by F and G? F has order 2, G has order 3, and FGF inverse is G inverse. So which group is this resembling? Quickly tell me. This resembles D3, right? This is your R, this is your S. And S, R, S inverse is R inverse. Then the next question, a review question is, the number of subgroups of Z2025 equals
Tau of 2025.
yes. So what's the number? Tau of 2025?
Say 1 minute.
Yeah.
So 15.
Just okay, fine. Let me see. Yeah. So the point is 2025, you have to write down its prime factors. So the beauty of this year is that 2025 is 45 squared. And 45 turns out to be a triangular number. It's 1 plus 2 plus dot 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 till 10, sorry, 9. So it's really beautiful. And 45 is 5 times 3 square. So this is 3 power 4 times 5 square. So now you add 1 to all these powers and multiply them together. So 4 plus 1 times 2 plus 1, that's 5 times 3 is 15. So you were right. The number of subgroups of Z 2025 is 15. Now, so final two questions. Find two distinct Stelo P subgroups of GL2FP. So can somebody tell me what are some Stelo P subgroups of GL2FP? So how does one start? One starts by writing down the order. What's the order of GL2FP?
Sir, it is Pn.
Yeah, P square.
Minus 1. So minus P actually.
Yeah.
And then P square minus 1.
Yes. So how many powers of P can you pull out from this? So there's definitely one P which can be pulled out from this, and what's left is P minus 1 and P square minus 1. And P doesn't divide these two, so you can only pull out one power of P. That means order of a silo P subgroup of GL2FP is
P.
yes, only P, not P square, not P cube, just P. So now tell me some subgroups of GL2FP of order P. One of them you already know. What is that?
So GL2, Z2.
What? One of them is U2. Just so that there is no confusion, I'll write U2FP. Is the subgroup of this form 1U01. Okay. So can you do something similar? Can you tell me a different P silo subgroup of GL2FP? So I took upper triangular matrices over here, right? So what else can you take? Yes, lower triangular matrices with diagonal 1. That's denoted by U2 bar FP, which is the set of all 1, 0, let's call it U prime 1, such that U prime is in FP. Both of these are Silo P subgroups of GL to FP. But by Silo's second theorem, these two should be conjugate. So check this element 0, 1, 1, 0 takes one to the other. Okay? Is this clear?
Yes, sir. Yes.
Okay. And the final question. Find the number of Silo P subgroups of SP. SP is the permutation group on P symbols. So we saw that Silo P subgroups of SP have order P, right? In the previous on the previous slide.
Yes, sir.
Now tell me all subgroups of SP of order P. How many of them are there?
So P minus 1.
So there are huge. There are many of them, not just P minus 1. So you have to look at first the number of order P elements in SP. That's like counting the P cycles in SP. And then note that P minus 1 of them generate the same subgroup. So the number of elements in SP of order P equals so this is like that basic problem in statistics, right? Uh, how many ways are there to arrange P people around a circular table?
So P minus 1 factorial.
Exactly. So P minus 1 factorial, the number of elements in SP of order P are P minus 1 factorial. You can check this. The point is you just have to create a P cycle that's possible in P factorial number of ways, right? Because the first entry has P choices, then the second entry has P minus 1 choices, dot, dot, dot. The last entry will have one choice, a single choice. So that means there are P factorial ways of arranging things here, but then you note that 1, 2, dot, dot, dot till P is the same as 2, 3, dot, 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 P1. So any cyclic rearrangement of these gives you the same permutation. So that's why this problem is analogous to that basic stats problem. And the answer from there is p minus 1 factorial. Now you note that um, p minus 1 of these generate the same subgroup, because 1 2 dot 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 till p will generate the same subgroup as its square, which will generate the same subgroup as its p minus 1th power. And this happens for any p cycle. So the number of silo or the number of subgroups of SP of order p are p minus 1 factorial divided by p minus 1, right? So that's p minus 2 factorial. Is this visible? I hope it's visible. Maybe I'll write it here. Okay, the number of subgroups of SP of order p are these. So that's the same as fellow p subgroups of SP But what do you know? You know from Silo's third theorem that this number is congruent to 1 mod p, right? If you remember, Silo's third theorem says that the number of Silo p subgroups of a group is congruent to 1 mod p. So this implies that p minus 2 factorial is congruent to 1 mod p multiplying by p minus 1 on both sides, you'll get p minus 1 factorial is congruent to minus 1 mod p, which is, what is the name of this theorem?
Fermat's little
Chinese,
No, Fermat's little
Chinese,
theorem is something else.
it's a
Uh-huh.
Chinese remainder theorem. Chinese remainder theorem.
No, Chinese remainder theorem is
Wilson
something.
theorem.
Yeah, so the college who is conducting this session, Wilson's theorem. I would like to end my sessions on Wilson's theorem.
Sir, could you explain that line, like the generator, in the generator that is written up to 1 to p, then 1 to p square, then 1 to p minus 1?
Yeah, so I am claiming that if you have an element sigma, which is a p cycle, then its square generates the same subgroup. So this this is a consequence of the following lemma. If sigma in G has order n, then this subgroup generated by sigma power m is the same as sigma for any m coprime to n. The point is, the order of the element sigma power m turns out to be n itself. This is implied by the fact that order of sigma power m equals n divided by the GCD of m and n. But if m and n are co-prime, then the GCD is 1 and order of sigma power n m is n. So The subgroup generated by sigma power m is of size n and is contained in the subgroup generated by sigma, but the sizes match and therefore there is an equality.
Okay, sir.
Okay.
Sir,
Yeah.
sir, sometimes we know the theorem, but we can't apply the theorem in question.
Okay.
Then how to compute the question? And we
Yeah.
can,
Right. So, yeah, you don't need to remember these theorems. Uh, the truth is, you don't need to remember these theorems. What you need to remember is the concept behind them. So, these Silo's theorems will look difficult. Even for me, they were difficult when I first saw them. But yeah, once you look at their proof and try to internalize the proof and the concepts behind the proof, these will become fairly clear to you. Next, if you're only concerned with using this to crack the JAM exam, then I would suggest a lot of problem solving. So try to solve as many problems as you can. Then these will come to you naturally.
okay, sir.
Try to see what are the uses of these theorems. There are many problems like show that if G is a group of order, let's say 99, then G has a non-trivial normal subgroup. For that, um, you use these theorems. You factorize 99 as 3 square times 11. Look at a Silo 11 subgroup. Try to compute the number of Silo 11 subgroups and whatnot. When you want to classify groups of order 99, then definitely you need all of these.
And so we need more classes from your side, sir.
Oh, okay. So on which topics you want classes? I'd be happy to give you lectures, but let's fix some topics. So which topics? Tell me.
Sir, I'm thinking about topic.
Okay, okay.
One or two practice sessions will also be helpful.
Sure, practice sessions is one idea.
Answer function of several variable.
Yeah, but that's a different instructor's thing, right? So it wouldn't be good if I invaded their area.
Are there any other doubts apart from extra sessions which you all are requesting? If there are no doubts, we would like to
So I have
proceed with
one
the vote of
question.
thanks. Yeah, go ahead.
Sir, hello.
Yeah.
Sir, is it possible if we can solve any question by using some concepts which are not in the IT JAM exam syllabus? Then can we solve any question using those concepts in the exam?
Sorry, I didn't get your question. What? You want to
Sir,
solve some questions in IIT Jam using concepts not in IIT Jam.
not in the syllabus. If is it possible to solve that particular question, then can we do that?
In the practice sessions, you're asking?
No, in the exam. Suppose one question came which
Mm-hmm.
we can solve by using something which is not in the syllabus. So can we do that?
Definitely.
Okay.
IIT Jam is an MCQ, right? So it doesn't matter how you arrive at the answer. You might as well be just guessing the answer, right? They don't care. The final answer is what is important in the exam.
Okay.
So definitely, if you have a different way of approaching the problem, which is outside the realm of the syllabus suggested by the website, definitely go for it.
Okay. Thank you, sir.
Sir,
Okay, so
sir,
Yeah,
it
is
is
there a doubt?
sir, it is easy to understand the definition that is given in the GEM syllabus of group theory, and then understanding the theorems. But when it comes to applying on question, sir, it gets more difficult. And then what's to remember, how to apply. So, what is the approach to deal such kind of problem?
Yeah, so what I did was problem solving. So I had this really good instructor who gave me a problem the morning I entered my college, and he expected me to solve the problem by the end of the day. So one problem every day, that was good enough for me to get a grasp on these concepts. So the main idea is problem solving. A human mind is such that you don't remember things that you just read, you remember things which you apply, right? So which you use. So once you read a section or a chapter in any book like Galleon or anything, try to solve the problems given at the end of that chapter. Try to apply your knowledge to solve some problems that will help you remember these theorems or the concepts. And that applies to all branches of mathematics. Doesn't matter group theory or linear algebra or whatever.
Okay, sir. Thank you, sir.
are there any more questions?
Sir, can you suggest some books for solving problems on group theory?
Yeah, so I did Galleon. I read Galleon and I solved many problems in it. Galleon is a good book.
Sir, there is so many questions in Galleons, but solutions is not provided there.
Yeah, so that's it, right? You have to discover the solutions yourself. You cannot just go at the back of the book and read the solutions. That won't help you.
So for the verification, and there are some questions when we try our 100%, then we need some solutions, some hints, something like that.
Yeah, so what you can do is you can show your professors the solution and they can validate it for you. They'll tell you if they can see an error or it's correct. That's the quickest way to do these things. Otherwise, you can make study groups and try to solve problems and pitch the solutions to others. Others will check. The best way is approach your professor.
Okay, sir.
I hope there are no more queries. So, on behalf of Department of Mathematics, Wilson College, I extend our sincere gratitude to Dr. Anand Chitrao, sir, for delivering 4 insightful sessions on group theory. Your clear explanations and systematic approach have greatly enhanced our students' understanding of the subject, sir. We truly appreciate the time, effort, and dedication you have devoted to this initiative. Thank you once again, sir, for accepting our invitation and providing valuable contribution to the success of this lecture series. Dear participants, we request your feedback for sir's session. The link for the same is posted in the chat box.
Yeah, thank you, Wilson College, to give me an opportunity to speak in front of many people, and thanks everybody for attending. I can see many of these
Thank you,
people
sir.
attending regularly. Best of luck for your JAM exams. Okay, then.